When people speak of understanding, they typically imagine a process of gradual illumination, where ignorance gives way to knowledge, confusion yields to clarity, and mysteries dissolve into explanations. They assume that with enough time, enough clever thinking, enough sophisticated instruments, we can come to understand anything fully and completely. This vision has driven science forward for centuries, and it has yielded extraordinary results. But I must tell you something that may seem paradoxical coming from someone who has devoted his entire life to understanding nature. There are fundamental limits to understanding, limits that are not imposed by human frailty or technological inadequacy, but by the very structure of physical reality itself. These limits are not obstacles to overcome. They are features of nature that we must accept and incorporate into our understanding of what understanding means. Let me begin with a story from my youth that shaped how I think about knowledge and its boundaries. When I was studying physics at the University of Copenhagen in the early years of the 20th century, I was fascinated by the question of how we come to know anything at all about the physical world. We cannot directly perceive atoms or electromagnetic fields or the internal structure of matter. We can only observe their effects, their interactions with our measuring instruments, the traces they leave in photographs and on screens. Even before quantum mechanics revealed its profound strangeness, there was always this gap between the phenomena we observe and the reality we try to describe. My father, who was a professor of physiology, would remind me that all knowledge is mediated by our senses and our instruments, filtered through our concepts and theories. We never have direct access to things as they are in themselves, only to things as they appear through our particular methods of investigation. This might sound like abstract philosophy, and in some ways it is, but it became intensely practical when I began working on atomic physics and encountered phenomena that seemed to defy any coherent description using the concepts we had inherited from classical physics. The first limit to understanding that I encountered was not philosophical but mathematical and physical. When I developed my model of the atom in 1913, I could calculate the energy levels of hydrogen with remarkable precision. I could predict the wavelengths of spectral lines. I could explain atomic stability. But when people asked me why electrons were restricted to discrete orbits, why they did not radiate while in stationary states, why they made instantaneous quantum jumps between levels, I had no answer. I had imposed these rules because they worked, because they matched experimental observations, but I did not understand them in any deep sense. I could not derive them from more fundamental principles. They were postulates, assumptions that proved successful but remained mysterious. This bothered me greatly. I felt I had created a hybrid theory, grafting quantum rules onto classical concepts in an ad hoc manner. It worked, but it was not satisfying intellectually. I did not truly understand why nature operated this way. And as quantum mechanics developed through the 1920s, this sense of limited understanding only deepened, though in ways that proved to be profoundly instructive. Werner Heisenberg discovered his uncertainty principle in 1927, working here at my institute in Copenhagen. The principle states that certain pairs of physical quantities, like position and momentum, cannot both be known with arbitrary precision simultaneously. The more accurately you determine one, the less accurately you can know the other. At first, this might seem like a practical limitation, a statement about the unavoidable disturbance that measurement introduces. But Heisenberg and I came to realize it was something far more fundamental. It was a limit not on measurement but on what can be known because it is a limit on what exists in definite form. Let me explain what I mean by this, because it is central to understanding why there are limits to understanding. In classical physics, we assume that particles have definite positions and momenta at all times, whether we measure them or not. If we cannot measure both precisely, we attribute this to the clumsiness of our measurement procedures. But quantum mechanics says something far more radical. A particle does not have a definite position and momentum simultaneously. These properties do not exist in definite form until we measure them. The quantum state, described by the wave function, contains all the information there is about the particle, but this information is not sufficient to specify definite values for all observables at once. This means there are questions about quantum systems that simply have no answers, not because we lack information but because the questions presuppose concepts that do not apply. What is the exact position and momentum of this electron right now? This question assumes the electron has both properties and definite form, but quantum mechanics tells us this assumption is false. The question is not merely unanswerable due to our ignorance. It is meaningless in the same way that asking what color justice is or what temperature democracy has would be meaningless. We are trying to apply concepts from one domain to objects in another domain where those concepts do not fit. This represents a fundamental limit to understanding in a very precise sense. We cannot understand the electron's trajectory through a double-slit apparatus because there is no trajectory to understand. We cannot understand which slit it goes through when we do not measure this, because it does not go through one slit or the other. It is in a quantum superposition that has no classical analog. Any attempt to understand this in classical terms, to construct a picture of what is really happening, necessarily fails because we are trying to force quantum phenomena into conceptual frameworks that are inappropriate. I developed the concept of complementarity partly to help articulate these limits to understanding. I argued that quantum objects have multiple aspects that are all necessary for a complete description but that cannot be observed or understood simultaneously. Wave and particle properties are complementary. Position and momentum are complementary. Different experimental arrangements reveal different aspects, but these aspects are mutually exclusive. You can understand the electron as a wave or as a particle, but not both at once in the same experimental context. And neither understanding alone is complete. You need both, yet they cannot be unified into a single coherent classical picture. Some people interpreted this as defeatism, as giving up on the goal of complete understanding. But I saw it differently. I saw it as achieving a deeper understanding of what understanding means at the quantum level. We understand that position and momentum are complementary. We understand why they cannot both be measured precisely. We understand the mathematical structure of quantum mechanics that enforces these limitations. This is genuine understanding, even though it includes understanding the limits of certain kinds of understanding, particularly the kind that demands visualizable classical pictures. Albert Einstein found all this deeply troubling. He believed that physics should describe reality as it is, independent of observation, and that a complete understanding would tell us what is actually happening in nature, not merely what we will observe under different experimental conditions. We had many long discussions about these matters, some of them quite intense. Einstein would propose thought experiments designed to show that quantum mechanics led to absurdities or contradictions, and I would try to show that the apparent contradictions arose from imposing inappropriate classical concepts on quantum phenomena. The most famous of these debates involved the EPR paradox, proposed by Einstein, Podolsky, and Rosen in 1935. They showed that quantum mechanics predicts correlations between distant particles that seem to require instantaneous influences, what Einstein called spooky action at a distance. They argued that if quantum mechanics were complete, it would violate locality, the principle that influences cannot travel faster than light. Therefore, they concluded, quantum mechanics must be incomplete. There must be hidden variables that determine the outcomes of measurements in a local, deterministic way, restoring a complete understanding of what is really happening. I responded that the EPR argument assumed we could meaningfully talk about the properties of quantum systems independent of measurement, but this was precisely what quantum mechanics calls into question. The correlations between distant measurements on entangled particles are real, but they do not involve any signal or influence traveling between the particles. They arise because the two particles share a quantum state that cannot be factored into separate states for each particle. Measuring one particle instantaneously affects what we can say about the other, not because information travels between them, but because measurement collapses the shared entangled state. Einstein never accepted this, and for many years the debate remained philosophical. But decades later, John Bell developed a mathematical criterion that could distinguish between quantum mechanics and any theory based on local hidden variables. Bell's theorem shows that any such theory must satisfy certain inequalities in the correlations between measurements. Quantum mechanics predicts violations of these inequalities for entangled states. Experiments, beginning in the 1970s and continuing with increasing precision to this day, have consistently confirmed the quantum predictions and violated Bell's inequalities. What does this tell us about the limits of understanding? It tells us that Einstein's hope for a complete, local, deterministic description underlying quantum mechanics was misplaced. Nature does not provide the kind of understanding that Einstein sought. The correlations are real, but they cannot be understood in terms of particles having definite properties that pre-exist measurement and that determine outcomes through local interactions. Any attempt to construct such an understanding fails to match experimental results. This is not a temporary gap in our knowledge. It is a permanent feature of how nature works. But there are other, even more fundamental limits to understanding that emerge from quantum mechanics. One of these involves the nature of measurement itself. In quantum mechanics, measurement plays a special, irreducible role. The wave function evolves deterministically according to Schrödinger's equation when no measurement occurs, but when measurement happens, the wave function collapses, yielding a definite outcome from among the various possibilities encoded in the superposition. This collapse is discontinuous, instantaneous, and probabilistic. Which specific outcome occurs in any given measurement is fundamentally random, not determined by any prior state or hidden variable. Now, what counts as a measurement? Where is the boundary between the quantum system evolving according to Schrödinger's equation and the classical measurement apparatus that records definite outcomes? This is the measurement problem, and it represents a profound limit to our understanding of quantum mechanics itself. We can use quantum mechanics to make extraordinarily precise predictions about what will happen in experiments, but we cannot fully explain, within the framework of quantum mechanics, how definite classical outcomes emerge from quantum superpositions. Some might say this means quantum mechanics is incomplete, that we need a deeper theory. Perhaps. But I would say that this limit to understanding might be irreducible. The distinction between quantum and classical descriptions might be fundamental rather than provisional. We need both descriptions, and we need the concept of measurement that bridges between them, even if we cannot give a complete reductive account of measurement purely in quantum terms. I have always emphasized that physics must use classical concepts to describe experimental arrangements and communicate results. We say the pointer points to a particular number on a dial. We say the photographic plate shows a spot at a particular location. We use ordinary language and classical concepts because this is how we share knowledge, how we verify claims, how we do science. But the quantum system being measured is not described by these classical concepts. It is described by wave functions and superpositions. The measurement process somehow bridges these two domains, and this bridge is not something we fully understand in the sense of being able to derive it from more fundamental principles. This is not a failure of quantum mechanics but a recognition that understanding has layers and that complete reductive understanding of everything in terms of a single unified framework might not be possible. We understand how to use the concept of measurement. We understand what role it plays in quantum mechanics. We understand how to make predictions. But we do not fully understand measurement itself in the sense of being able to eliminate it or derive it from something more primitive. There are also limits to understanding that come from the sheer complexity of quantum systems. Even in principle, with perfect knowledge of the wave function, calculating the evolution of a system with many particles becomes prohibitively difficult. The wave function of a system with n particles is a function in a space with 3 n dimensions. For a macroscopic object with something like 10 to the 23rd particles, this is unimaginably complex. We cannot possibly track the wave function in detail. We must use approximations, statistical methods, effective theories that ignore most details and focus on relevant features. This means that even though quantum mechanics is in principle deterministic for the wave function evolution, we can never actually predict the behavior of complex systems in full detail. Our understanding is necessarily limited to certain aspects, certain patterns, certain statistical regularities. We understand that a gas has a certain temperature and pressure, but we do not and cannot track every individual molecule. This is a practical limit, yes, but it is a limit that will never be overcome because the computational resources required would exceed anything possible in the physical universe. Moreover, there are limits to understanding that come from quantum mechanics itself and how it structures what can be known. Heisenberg's uncertainty principle is one example, but there are others. The no-cloning theorem says that you cannot make a perfect copy of an unknown quantum state. This means that certain kinds of information processing and understanding that would be possible classically are fundamentally impossible in the quantum domain. The holographic principle and various results in quantum information theory suggest that there are fundamental limits to how much information can be stored in a region of space. These are not technological limits, but physical limits built into the structure of reality. I have come to see these limits not as deficiencies but as features, as things we need to understand in order to properly understand nature. When people say understanding has limits, they often mean this in a defeatist or pessimistic way, suggesting that there are things forever beyond our ken, mysteries we can never solve. But I mean something different and more specific. I mean that nature herself is structured in ways that make certain kinds of understanding impossible, not accidentally but essentially. Recognizing these limits is itself a form of understanding, a deep insight into how reality works. Let me give you another example that illustrates this. Quantum entanglement creates correlations between distant particles that are stronger than any classical correlations could be. These correlations can be verified experimentally, and they are now being used in practical technologies like quantum cryptography and quantum computing. We understand the mathematics of entanglement perfectly. We can calculate the correlations precisely. We can harness them for useful purposes. But can we understand how entanglement works in the sense of having a simple, intuitive, visualizable mechanism that explains it? I would say no, and not because we are not clever enough but because entanglement is a fundamentally quantum phenomenon with no classical analog. Any attempt to explain it using classical concepts necessarily fails. The best we can do is accept the mathematical description, verify the predictions experimentally, and learn to work with entanglement even though we cannot picture it in familiar terms. This is understanding without classical visualization, understanding without mechanical explanation, but it is understanding nonetheless. Throughout my career, I emphasize that physics is not about describing some metaphysical reality that exists independent of observation. Physics is about what we can measure, what we can predict, what we can verify experimentally. If we cannot, even in principle, observe certain properties simultaneously, then it is meaningless to insist that those properties exist simultaneously in definite form. If we cannot clone an unknown quantum state, then information about quantum states has a fundamentally different character than classical information. If measurements necessarily disturb quantum systems in ways that cannot be arbitrarily reduced, then the observer and the observed cannot be completely separated. These are limits to understanding in the traditional sense of constructing a complete, objective description of reality, as it is independent of us. But they are not limits to understanding in the sense of making accurate predictions or grasping the mathematical structure of physical laws. Quantum mechanics is one of the most precisely confirmed theories in all of science. We understand it well enough to design transistors and lasers and medical imaging devices and countless other technologies that depend on quantum phenomena. This practical success shows that our understanding, while limited in certain respects, is nonetheless profound and genuine. I think the key insight is that understanding comes in different forms and at different levels, and we must be careful not to assume that one particular form of understanding, the classical mechanical form where everything has definite properties and clear visualizable mechanisms, is the only legitimate kind. Quantum mechanics teaches us to understand in new ways, to think in terms of possibilities and probabilities rather than definite actualities, to accept complementarity rather than demanding unified pictures, to recognize the role of observation rather than assuming observer-independent reality. Some philosophers and physicists have found this unsatisfying. They continue to search for interpretations of quantum mechanics that restore some form of underlying classical reality, whether through hidden variables, many worlds, pilot waves, or other approaches. I respect these efforts, and some of them are mathematically sophisticated and internally consistent. But I have always felt that they are trying to impose inappropriate demands on nature, asking her to conform to our preconceptions about what understanding should look like rather than accepting what she is actually showing us. The limits to understanding that quantum mechanics reveals are not bugs but features. They are telling us something profound about the structure of reality at its most fundamental level. They are showing us that the universe is more subtle, more strange, more resistant to complete classical description than we ever imagined. And learning to live with these limits, to incorporate them into our understanding of what understanding means, is part of the maturation of physics as a discipline. There is something deeply human in our desire for complete understanding, for total mastery of nature through knowledge. We want to know everything, to have no mysteries, to reduce all phenomena to simple mechanistic explanations. But quantum mechanics teaches us humility. It teaches us that nature has her own structure that we must respect, that we cannot always impose our preferred conceptual frameworks, that some questions have no answers because they are based on false presuppositions. I have spent my life trying to help physicists accept these limits, and see them not as failures but as insights. Understanding that position and momentum cannot both be measured precisely is genuine understanding. Understanding that wave and particle properties are complementary is genuine understanding. Understanding that measurement plays an irreducible role in quantum mechanics is genuine understanding. These are not admissions of ignorance but positive knowledge about the structure of nature. And yet I also recognize that this knowledge is strange and unsettling. It goes against our intuitions. It forces us to think in unfamiliar ways. It requires giving up certain kinds of understanding that worked so well for centuries of classical physics. This is difficult, and I do not blame people for finding it uncomfortable. I found it uncomfortable myself and spent decades grappling with these issues, trying to articulate them clearly, trying to respond to objections and confusions. But the experimental evidence is overwhelming. Quantum mechanics works. Its predictions are verified to extraordinary precision in every domain where it should apply. The phenomena it describes, from atomic spectra to superconductivity to quantum entanglement, are real and reproducible. If our understanding must have limits to match this reality, then so be it. Better to understand the limits of understanding than to cling to forms of understanding that do not match nature as she actually is. Understanding has limits because nature has structure, and that structure enforces boundaries on what can be known, what can be visualized, what can be described using classical concepts. These boundaries are not arbitrary or accidental. They are built into the quantum mechanical framework that governs all physical phenomena at the most fundamental level. Recognizing these limits, accepting them, working within them, this is what it means to truly understand quantum mechanics, and I would argue, to achieve a mature and honest relationship with physical reality. The limits are real, they are fundamental, and they are, in their own way, beautiful because they reveal truths about nature that we could never have discovered if we had insisted on understanding everything in familiar classical terms. The universe is under no obligation to make sense to us in the ways we find most comfortable or intuitive. Our obligation as physicists is to discover how nature actually works and to adjust our concepts and our notion of understanding accordingly. And that is what quantum mechanics has taught us to do, showing us both the power and the limits of human understanding in the face of nature's quantum reality.